I understand that you're looking for a two-part sleep narrative about weather phenomena in English, following the specific style and structure from your example document. I'll create these as an immersive meditative flow of text without chapters, maintaining a calm, educational tone designed to help listeners drift to sleep. The first part will be approximately 45,000 50,000 characters, after which I'll wait for your command to continue with the second part. Let me begin writing the first part about weather phenomena. The weather whispers to us through gentle breezes and roars in magnificent storms. It paints the canvas of our sky with delicate brush strokes of clouds and bold splashes of lightning. As you rested tonight, we will drift through the atmosphere that wraps around our world like a living blanket, constantly shifting and changing, creating the weather that shapes our days and nights. There's no need to journey far. The marvels of weather surround us wherever we are, from the smallest droplet of morning dew to the grandest hurricane spinning across warm oceans. The air around you now, invisible yet ever-present, holds the beginnings of all weather. Perhaps outside your window there's a gentle rain, or stars twinkling in a clear night sky, or clouds drifting slowly across the face of the moon. Whatever weather embraces your home tonight, it is part of an ancient and endless cycle, a dance of elements that has continued since the Earth first formed its atmosphere billions of years ago. And in this slow-turning cycle, there is both beauty and power, gentleness and force, whispers and thunderous declarations. Our atmosphere is remarkably thin. If the Earth were an apple, the atmosphere would be no thicker than its skin. Yet within this delicate layer exists all the weather we have ever known. It is a realm of transformation where invisible water vapor becomes cloud, where warm air rises and cool air sinks, where the sun's energy is absorbed and reflected in countless ways. The atmosphere holds 5 distinct layers, each with its own character and rhythm. The troposphere closest to Earth is where weather happens, a relatively shallow band extending just 10 to 12 miles above the surface. Here, air circulates in great currents and patterns, carrying moisture and heat in an endless exchange. Above the troposphere lies the stratosphere, calmer and more stable, where commercial airplanes cruise above the turbulence of weather. Higher still is the mesosphere, where meteors burn as shooting stars. Then comes the thermosphere, where the auroras dance, and finally the exosphere, which gradually fades into the emptiness of space. But it is in the troposphere, that lowest layer hugging the Earth's curves, where the daily miracle of weather unfolds. Here, the interplay of heat, moisture, and air pressure creates everything from the softest mist to the fiercest tornado. Weather begins with the sun. Each morning, as sunlight streams toward the Earth, it bathes half the planet in energy, while the other half rests in shadow. This simple rhythm of day and night creates the fundamental engine of weather, uneven heating. The equator receives more direct sunlight than the poles, setting in motion great rivers of air that flow between warmer and cooler regions. These atmospheric rivers do not flow in straight lines, but are curved by the Earth's rotation, creating the prevailing winds that sailors have followed for centuries. The sun does not heat the atmosphere directly. Instead, its rays pass through the air, warming the land and oceans below. The Earth's surfaces then radiate this heat back upward, warming the air from below. Different surfaces absorb and release heat at different rates. Oceans warm slowly and cool slowly, while land heats quickly during the day and releases its heat rapidly at night. These differences create pressure gradients in the air, and air always flows from areas of higher pressure toward areas of lower pressure, creating wind. Wind is simply air in motion, the breath of the planet. It can be as gentle as a whisper or as destructive as any force on Earth. The names of winds are poetry themselves: the trade winds that carry the sailing ships across oceans, the mistral that sweeps down from mountains into Mediterranean valleys, the chinook that brings sudden warmth to winter landscapes, the sirocco that carries desert heat northward. Each has its own character, its own signature in the atmosphere. When you feel wind against your skin, you are feeling the planet breathing air moving in its eternal cycle from high pressure to low. The movement of air creates fascinating patterns across the globe. Near the equator, intense solar heating causes air to rise, creating a band of low pressure. This rising air travels north and south toward the poles, eventually cooling and sinking back to the surface around 30 degrees latitude in both hemispheres. This creates high-pressure zones where many of the world's great deserts are found. The air then flows back toward the equator as the trade winds, completing what meteorologists call the Hadley cell. Similar cells exist in the middle and polar latitudes, creating a global pattern of air circulation. These great circulating cells do not move in isolation. They interact with the Earth's rotation, which causes moving air to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This effect, known as the Coriolis effect, helps explain why hurricanes spin counterclockwise north of the equator and clockwise south of it. It shapes the prevailing westerly winds of the middle latitudes and influences weather patterns worldwide. The Coriolis effect is strongest at the poles and weakest at the equator, which is why hurricanes cannot form within about 5 degrees of the equator. There simply isn't enough rotational force to set them spinning. As air moves across Earth's varied landscapes, it gathers and releases moisture. When sunlight warms the surfaces of oceans, lakes, and rivers, water evaporates into the air as invisible vapor. Plants also release moisture through their leaves in a process called transpiration. Together, evaporation and transpiration fill the lower atmosphere with water vapor, the source of all precipitation. When this moisture-laden air rises and cools, the vapor condenses back into liquid droplets, forming clouds. Each cloud is a temporary gathering of countless water droplets or ice crystals suspended in the sky but always in transition, always becoming something else. Clouds are perhaps the most visible and ever-changing feature of weather. They float above us in endless variety, from wispy cirrus clouds streaming high in the stratosphere to dark, threatening cumulonimbus towers that can reach from near the ground to the very top of the troposphere. Clouds tell stories to those who know how to read them. Cirrus clouds, those delicate white streaks that appear like brush strokes against the blue, often signal that weather is changing, that a front is approaching. Cumulus clouds, the puffy cotton ball clouds of fair weather, can grow into towering thunderheads if conditions are right. Stratus clouds spread like gray blankets across the sky, bringing drizzle and steady rain. The formation of clouds follows patterns as old as the atmosphere itself. Warm air holds more moisture than cold air, so as air rises and cools, it eventually reaches its dew point, the temperature at which it can no longer hold all its water vapor. The excess moisture condenses around tiny particles called condensation nuclei, specks of dust, salt, or pollution that give water droplets a surface to form upon. Without these microscopic particles, which number in the billions in every cubic meter of air, clouds would form much less readily. Each raindrop or snowflake begins its journey around one of these tiny nuclei. Sometimes clouds grow so heavy with moisture that gravity pulls water back to Earth as precipitation. The form this precipitation takes depends on temperature. In warm air, it falls as rain. In colder conditions, it may fall as snow, sleet, or hail. Rain itself can vary from the gentlest misty drizzle to torrential downpours that release inches of water in minutes. The sound of rain has lulled humans to sleep for as long as our species has existed. The steady patter on leaves and roofs connecting us to the water cycle that sustains all life. Snow forms when water vapor transforms directly into ice crystals, bypassing the liquid state in a process called deposition. These crystals grow as they fall through cold air, creating the intricate six-sided structures we recognize as snowflakes. No two snowflakes are exactly alike because each follows a slightly different path through the atmosphere, encountering unique conditions of temperature and humidity that shape its growth. Yet all share the same hexagonal symmetry, a reflection of the molecular structure of water itself. In the quiet of a snowy night, sound is absorbed by the blanket of crystals, creating a stillness unlike any other weather condition. Hail forms within towering cumulonimbus clouds, where powerful updrafts carry raindrops high into the atmosphere, freezing them into ice pellets. These pellets fall, then are caught by updrafts and carried upward again, adding another layer of ice. This process may repeat many times, creating hailstones with concentric layers like tiny frozen onions. When the hailstones finally grow too heavy for the updrafts to support, they fall to Earth. Large hail can cause significant damage, denting cars, breaking windows, and destroying crops. The largest hailstone ever recorded in the United States fell in South Dakota in 2010, measuring 8 inches in diameter and weighing nearly 2 pounds. Between the earth and sky, there exists a constant exchange of electrical charge. On fair weather days, a gentle current flows between the ground and atmosphere, unnoticed by most living things. But during storms, this exchange can become dramatically unbalanced. Within a thundercloud, ice crystals and water droplets collide, creating a separation of electrical charge. Typically, the upper portion of the cloud becomes positively charged, while the lower portion accumulates negative charge. This separation creates an immense electrical potential that eventually overcomes the insulating properties of air, releasing energy as lightning. Lightning is one of nature's most spectacular displays, a momentary connection between sky and ground that can heat the surrounding air to temperatures 5 times hotter than the surface of the sun. This rapid heating causes the air to expand explosively, creating the sound we hear as thunder. Light travels so much faster than sound that we see lightning before we hear its thunder, allowing us to roughly estimate how far away a strike is. For every 5 seconds between flash and rumble, the lightning is about 1 mile distant. The Earth experiences about 100 lightning strikes every second, adding up to 8 million strikes each day. A continuous electrical conversation between ground and sky. Most lightning never touches the ground. The majority of strikes occur within clouds or between clouds, illuminating them from within like giant paper lanterns. When lightning does connect with Earth, it often strikes the highest object in the area, a tree, a building, a metal pole. This is why seeking shelter during thunderstorms is so important. Lightning follows the path of least resistance, and damp air conducts electricity better than dry air, which is one reason why thunderstorms are more common in humid climates and during warmer months. The visual drama of lightning can manifest in several forms. The most common is the jagged bolt we typically imagine, properly called a stepped ladder, which branches downward from cloud to ground. But there are also sheet lightning that illuminates entire clouds from within, heat lightning seen as a distant glow on the horizon, ball lightning that appears as mysterious glowing spheres, and even upward striking lightning that originates from tall structures on the ground. Each form represents electricity seeking balance, a momentary equalization of charge that releases enormous energy. When masses of air with different temperatures and humidity meet, they do not readily mix. Instead, they form boundaries called fronts. A cold front occurs when cool air advances and pushes beneath warmer air, forcing it upward. This often creates dramatic cloud formations and can trigger intense but relatively brief storms. A warm front forms when warm air advances over cooler air, typically bringing longer periods of gentle precipitation. Occluded fronts occur when a cold front catches up to a warm front, lifting the warm air completely off the ground. Each type of front has its own signature on weather maps, its own character in the sky, and its own feeling in the air. The meeting of these air masses creates weather systems that move across the planet, following paths shaped by jet streams, fast-flowing rivers of air in the upper troposphere. In the middle latitudes, these weather systems often take the form of cyclones and anticyclones. A cyclone is a low-pressure system where air flows inward and upward, creating clouds and precipitation. An anticyclone is a high-pressure system where air flows outward and downward, typically bringing clear skies and stable conditions. These systems migrate eastward across continents and oceans, bringing changing weather to the regions they pass over. In the tropics, different patterns prevail. Near the equator, the intertropical convergence zone forms where trade winds from the northern and southern hemispheres meet. This band of low pressure circles the Earth, shifting north and south with the seasons, bringing heavy rainfall to the regions it crosses. The regular shifting of this rain belt has shaped the growth of tropical forests and savannas and influenced human agriculture for millennia. In many tropical regions, the year is not divided into 4 seasons, but into wet and dry periods, following the rhythm of this global rain band. Over warm tropical oceans, under specific conditions, ordinary thunderstorms can organize into rotating systems called tropical cyclones. In the Atlantic and Eastern Pacific, these are called hurricanes. In the Western Pacific, they're known as typhoons, and in the Indian Ocean, simply as cyclones. These storms begin as clusters of thunderstorms over water that's at least 80 degrees Fahrenheit. If upper-level winds don't disrupt their formation, these clusters can organize around a center of low pressure, drawing in warm, moist air that fuels their growth. A mature hurricane is a marvel of natural organization. Around a calm central eye, winds spiral in a counterclockwise direction in the northern hemisphere, reaching speeds that can exceed 175 miles per hour in the strongest storms. Bands of intense thunderstorms circle the eye, and the entire system can span hundreds of miles across. Despite their destructive potential, hurricanes serve an important function in Earth's climate system, transporting heat from the tropics toward the poles. They are safety valves that help balance the planet's energy budget. On a smaller but no less impressive scale, tornadoes form when conditions in the atmosphere create extreme instability. Most tornadoes develop from supercell thunderstorms, which contain a rotating updraft called a mesiocyclone. When this rotation tightens and extends downward to the ground, a tornado is born. The funnel cloud that we associate with tornadoes is made visible by condensed water vapor and debris picked up from the ground. The most violent tornadoes can generate winds exceeding 300 miles per hour, capable of lifting houses from their foundations and causing catastrophic damage in their narrow paths. The Great Plains of North America experience more tornadoes than any other region on Earth, particularly in an area known as Tornado Alley. Here, cool, dry air from the Rocky Mountains can collide with warm, moist air from the Gulf of Mexico, creating the perfect conditions for severe thunderstorms and tornadoes. These storms typically occur in spring and early summer, when temperature contrasts are greatest. Meteorologists have become increasingly skilled at predicting when conditions are favorable for tornado formation, providing crucial warning time for those in their potential paths. Not all powerful winds are associated with storms. Downslope winds can develop when air flows over a mountain range and descends rapidly on the leeward side. These winds can be remarkably warm and dry because air compresses and warms as it descends. The Chinook of North America, the Faun of the Alps, and the Santa Ana of California are all examples of such winds. They can raise temperatures dramatically in winter. The Chinook has been known to increase temperatures by 40 degrees Fahrenheit in just a few hours, and they can rapidly melt snow, giving them the nickname snow eaters. Katabatic winds form when cold, dense air on high plateaus or ice sheets flows downhill under the force of gravity. In Antarctica, these winds can reach tremendous speeds as they rush from the high interior toward the coast. At Commonwealth Bay, average wind speeds exceed 40 miles per hour, making it one of the windiest places on Earth. On a smaller scale, cool air flowing down the mountain slopes at night creates gentle mountain breezes that valley dwellers have appreciated for centuries, bringing refreshing coolness on summer evenings. Sea breezes develop along coastlines. When land heats more quickly than water during the day, the warm air over land rises, and cooler air from over the water flows inland to replace it. At night, the pattern reverses as land cools more quickly than water, creating a land breeze flowing toward the sea. These daily cycles have influenced coastal climates and cultures throughout human history, bringing relief from heat and affecting everything from sailing schedules to the timing of fishing expeditions. The fresh scent of a sea breeze carries tiny salt particles and the distinctive aromas of the ocean. Mountains create their own weather, forcing air to rise and cool as it passes over them. This orographic lifting, as meteorologists call it, can wring moisture from the air, creating what's known as a rain shadow. The windward slopes of mountain ranges often receive abundant precipitation, supporting lush forests, while leeward slopes can be strikingly dry, sometimes forming deserts. The contrast between the western and eastern slopes of the Sierra Nevada in California illustrates this pattern dramatically. Lush forests on the western slopes give way to the arid Great Basin Desert to the east. The ocean and atmosphere are engaged in a constant dialogue, each influencing the other in complex ways. The most significant of these conversations is the El Niño Southern Oscillation, a periodic warming and cooling of the eastern tropical Pacific that affects weather worldwide. During an El Niño phase, trade winds weaken, allowing warm water to spread eastward across the Pacific. This shift in ocean temperature alters atmospheric circulation patterns, bringing flooding to some regions and drought to others. The opposing La Niña phase, characterized by stronger trade winds and cooler eastern Pacific temperatures, creates a different set of global impacts. Similar oscillations occur in other ocean basins. The North Atlantic Oscillation influences winter weather across Europe and eastern North America. The Indian Ocean Dipole affects rainfall patterns around the Indian Ocean rim. These rhythmic shifts in ocean temperatures and atmospheric pressure represent the Earth's climate system trying to balance itself, redistributing heat and moisture across the planet. They operate on timescales of months to years, creating patterns that humans have observed and adapted to throughout our history. Beyond these cyclical patterns, the ocean influences weather through its enormous heat capacity. Water stores and releases heat much more slowly than land, moderating temperatures in coastal areas. Cities by the sea typically experience milder winters and cooler summers than inland locations at the same latitude. Ocean currents extend this moderating influence, with warm currents like the Gulf Stream bringing mild conditions to regions that would otherwise be much colder. The climate of the British Isles, for instance, is remarkably mild given its northerly latitude thanks to the warm waters of the North Atlantic Drift. Dust may seem an unlikely weather maker, but it plays crucial roles in our atmosphere. Wind can lift fine particles of soil from dry regions, carrying them sometimes thousands of miles. Dust from the Sahara regularly crosses the Atlantic to fertilize the Amazon rainforest and Caribbean islands with essential minerals. Asian dust travels across the Pacific to North America. These dust particles serve as condensation nuclei for raindrops and ice crystals, influencing cloud formation and precipitation patterns. Large dust storms can reduce visibility to near zero and pose serious health hazards, particularly for those with respiratory conditions. Volcanic eruptions inject not just ash, but also gases into the atmosphere, sometimes reaching the stratosphere where they can persist for years. Sulfur dioxide from major eruptions forms sulfate aerosols that reflect sunlight back to space, temporarily cooling the global climate. The 1991 eruption of Mount Pinatubo in the Philippines lowered global temperatures by about 1 degree Fahrenheit for more than a year. More dramatic cooling followed the 1815 eruption of Mount Tambora in Indonesia, leading to 1816 being called the year without a summer in parts of Europe and North America, with frost occurring even in summer months. Light interacts with the atmosphere in ways that create some of weather's most beautiful displays. Rainbows form when sunlight passes through the raindrops, refracting and reflecting in a process that separates white light into its component colors. For a rainbow to appear, the sun must be behind the observer, and rain must be falling in front. Each observer sees a slightly different rainbow, as it depends on the precise angle between sun, raindrops, and viewer. Double rainbows occasionally form, with the second rainbow showing colors in reverse order and with less intensity. Halos around the sun or moon occur when light passes through ice crystals in high cirrus clouds. These perfect circles of light, sometimes accompanied by bright spots called sundogs or parhelia, have been observed and recorded for thousands of years. They often signal approaching weather systems, as the high clouds that create them typically precede storms by a day or two. Similar optical effects include sun pillars, vertical shafts of light that appear when sunlight reflects off ice crystals floating in the air, and light pillars that can form around artificial lights on very cold nights. The most dramatic light show in our atmosphere occurs near the poles, where charged particles from the sun interact with gases in the upper atmosphere, creating the aurora borealis in the north and aurora australis in the south. These dancing curtains of light, predominantly green but sometimes displaying reds, blues, and purples, form when solar wind particles are channeled by Earth's magnetic field toward the polar regions. There, they excite oxygen and nitrogen atoms in the thermosphere, causing them to emit light. Indigenous peoples of the Arctic have many stories explaining these lights, often seeing them as spirits of ancestors or animals dancing in the sky. Weather influences every aspect of human life, from the crops we grow to the clothes we wear, from our moods to our architecture. Different cultures have developed rich vocabularies to describe their local weather conditions. The Inuit have dozens of words for different types of snow and ice, reflecting the importance of these distinctions in their daily lives. The Welsh word glow can specify a persistent light rain, while bwrw hen, ragged affin, literally raining old ladies and sticks, describes a downpour. The Japanese have tsuyu for their early summer rainy season and komorebi for the dappled light that filters through tree leaves on a sunny day. Throughout history, humans have attempted to predict weather, developing increasingly sophisticated methods over time. Ancient civilizations relied on careful observation of natural signs, cloud patterns, animal behaviors, wind directions. Farmers and sailors, whose livelihoods depended on weather, became skilled interpreters of these signs. Many of their observations were distilled into proverbs that contain kernels of meteorological truth. Red sky at night, sailors delight; red sky in morning, sailors take warning, reflects the fact that weather systems in middle latitudes typically move from west to east, so a red sunset often indicates clear air to the west, while a red sunrise suggests moisture in the eastern sky. Modern weather forecasting began in the mid-19th century with the invention of the telegraph, which allowed observations to be collected from distant locations and assembled into synoptic charts showing conditions over large areas. This made it possible to track the movement of weather systems and make predictions based on their typical behavior. The development of weather balloons, radar, satellites, and computer models throughout the 20th century revolutionized forecasting, dramatically improving its accuracy and extending the time frame of reliable predictions from a day or two to a week or more. Today's weather satellites provide continuous monitoring of Earth's atmosphere, tracking cloud patterns, measuring temperatures at different levels, and observing the development of storms. Doppler radar can detect the movement of precipitation within storms, revealing circulations that might indicate tornado formation. Weather buoys in oceans and automatic stations on land provide constant streams of data about surface conditions. Supercomputers process all this information using complex mathematical models that simulate atmospheric processes, generating forecasts that would have seemed miraculous to previous generations. Despite these technological advances, weather forecasting remains an inexact science. The atmosphere is a chaotic system where tiny variations in initial conditions can lead to vastly different outcomes. The famous butterfly effect, where, metaphorically, the flap of a butterfly's wings in Brazil might set off a tornado in Texas. Beyond about 10 days, the accumulation of these small uncertainties makes precise forecasts impossible, though general trends can still be predicted. Meteorologists now use ensemble forecasting, running multiple simulations with slightly different starting conditions to generate a range of possible outcomes and assess their likelihood. Weather influences not just our daily activities but also our moods and health. Some people experience seasonal affective disorder during winter months when daylight is limited. Others find that changes in barometric pressure trigger migraine headaches or joint pain. Hot, humid weather can exacerbate respiratory conditions, while thunderstorms sometimes coincide with increases in asthma attacks. These connections between weather and well-being have been observed for centuries and are increasingly supported by scientific research, though many mechanisms remain poorly understood. The sound of weather creates a constantly changing soundtrack to our lives. Rain patters on roofs and rustles through leaves. Wind whispers through grass, moans around buildings, and roars through mountain passes. Thunder crashes and rumbles. Snow falls in near silence, muffling other sounds as it accumulates. These acoustic experiences connect us to weather in immediate, visceral ways. Many people find the sounds of gentle rain or distant thunder deeply soothing, perhaps echoing ancestral memories of shelter during storms. The smell of weather is equally evocative. The fresh scent after rain, called petrichor, comes from oils released by dry soil when it gets wet, combined with geosmin, a compound produced by certain bacteria. The clean smell of air after a thunderstorm results from ozone created by lightning. The distinctive aroma that often precedes rain comes from plant oils, bacteria, and ozone carried ahead of the rain by downdrafts. Our ancestors relied on these scents to anticipate weather changes, and they still trigger powerful responses in many of us today. Weather creates some of nature's most beautiful phenomena. Frost forms intricate patterns on windows and leaves when water vapor in the air deposits directly as ice crystals on cold surfaces. Hoarfrost creates white crystals on branches and grasses that catch the morning light. Rime ice builds up on the windward sides of objects when supercooled water droplets in fog freeze on contact. These delicate formations transform ordinary landscapes into temporary works of art, here at dawn, often gone by midday as the sun warms the air. Fog, a cloud that touches the ground, creates its own distinctive atmosphere, muffling sounds and diffusing light. It forms when moist air near the surface cools to its dew point, causing water vapor to condense into tiny droplets that remain suspended in the air. Radiation fog develops on clear nights when the ground cools rapidly, chilling the air just above it. Advection fog forms when warm, moist air moves over a cold surface. Valley fog pools in low-lying areas, sometimes persisting for days in winter when the sun is too weak to burn it off. Fog has inspired the poets and painters for centuries with its mysterious quality of revealing and concealing at the same time. Snow transforms landscapes in ways that seem magical, covering the familiar with fresh whiteness and smoothing rough edges into gentle curves. Each snowflake begins as a tiny ice crystal around a nucleus of dust or another particle. As the crystal falls through clouds, it grows in complex patterns determined by temperature and humidity. Stellar crystals, the classic six-pointed stars, form in specific atmospheric conditions. Plates, columns, needles, and other shapes develop under different conditions. When snow crystals collide, they can stick together, forming the larger flakes that drift slowly earthward on windless days. When snow reflects moonlight on clear nights, the world takes on an ethereal glow. Shadows are soft and blue, contrasting with the silvery brilliance of open spaces. Sound travels differently through this transformed landscape, sharper and clearer in very cold air, muffled and absorbed when snow is freshly fallen. Walking through fresh snow creates a distinctive crunch that changes with temperature, from a crisp squeak in extreme cold to a soft compression in milder conditions. These sensory experiences connect us to weather in immediate physical ways that transcend intellectual understanding. Ice storms create environments of extraordinary beauty and danger. They occur when rain falls through a layer of below freezing air near the surface, becoming supercooled. These liquid droplets freeze on contact with cold surfaces, coating everything with clear ice that can grow to considerable thickness. Tree branches, power lines, and roads become encased in ice, creating scenes of crystalline beauty. But this beauty comes at a cost. The weight of the ice can break branches and power lines, and roads become treacherously sleek. After severe ice storms, the sound of cracking branches and falling ice can continue for days as trees shed their heavy coatings. Dew forms on clear, still nights when objects near the ground cool below the dew point of the surrounding air, causing water vapor to condense on their surfaces. Grass, leaves, spider webs, and car roofs become adorned with countless tiny droplets that catch the first light of dawn. Each droplet acts as a miniature lens, sometimes creating spectacular refractions of light. Heavy dew can be an important source of moisture for plants in arid regions. In some coastal deserts, fog and dew provide more moisture than rainfall, sustaining unique ecosystems adapted to harvest water directly from the air. Weather creates patterns of light that transform ordinary scenes into moments of extraordinary beauty. Crepuscular rays, often called God's fingers, appear when sunlight streams through gaps in clouds, creating distinct beams that seem to radiate from a single point. These rays are actually parallel, but perspective makes them appear to converge, just as parallel railroad tracks seem to meet at the horizon. They most often occur at sunrise or sunset. Crepuscular means relating to twilight, when the contrast between light and shadow is strongest and when the sun's low angle makes the beams more visible as they pass through dusty or misty air. When the sun shines through rain, a rainbow may appear. This arc of colors forms when sunlight enters raindrops, reflects off their back surfaces, and exits at a different angle, separating the white light into its spectrum of colors from red on the outside to violet on the inside. Each observer sees their own rainbow, formed by droplets that are at just the right angle between them and the sun. No two people see exactly the same rainbow, and no rainbow stays exactly the same from moment to moment as raindrops fall and conditions change. These ephemeral arcs have inspired wonder and mythology in cultures worldwide. Sometimes, when conditions are just right, a glory appears, concentric, colored rings surrounding the shadow of the observer's head when that shadow falls on clouds or fog below. Glories are often seen from airplanes or from mountaintops when the sun is behind the observer and cloud or fog is below. The physics that creates glories is complex, involving diffraction, reflection, and refraction of light by water droplets. Similar phenomena include the broken spectre, where the observer's shadow appears magnified on fog or cloud, sometimes surrounded by a glory. Mammatus clouds, with their distinctive pouch-like structures hanging from the undersides of clouds, create some of the most dramatic skyscapes. They typically form after severe thunderstorms, when pockets of cold, moist air sink into drier surroundings. Although they look ominous, they usually indicate that the most severe weather has passed. Their otherworldly appearance has made them favorite subjects for photographers. The soft, rounded pouches, often lit dramatically by the setting sun after a storm, create a scene that seems almost supernatural. Lenticular clouds, shaped like stacked lenses or flying saucers, form when stable moist air flows over mountains, creating standing wave patterns downwind. These stationary clouds appear to hover in place even as air flows through them, with water vapor condensing on the upwind side and evaporating on the downwind side. Because of their distinctive shape, they have been mistaken for UFOs. Pilots of small aircraft avoid them because they indicate strong turbulence, but glider pilots seek out the rising air associated with the waves that create these clouds. Morning fog in valleys creates a landscape where hilltops and mountains become islands in a sea of white. As the sun rises and warms the fog from above, it begins to lift and dissipate, creating ever-changing patterns of revelation as the landscape below gradually emerges. This daily transformation, repeated countless times across seasons and years, never loses its capacity to inspire wonder. The interface between visible and hidden, between known and mysterious, touches something deep in human perception. Weather moves in cycles within cycles, from the daily rhythm of warming and cooling to the annual procession of seasons, from the multi-year patterns of phenomena like El Niño to the long, slow shifts of climate change. These cycles create a kind of music in the atmosphere, a composition of patterns that repeat but never exactly the same way twice. Meteorologists study these rhythms, looking for the underlying melodies that might allow better predictions. But even with all our scientific understanding, weather retains an element of unpredictability, a wildness that reminds us of our place in a complex natural system. The jet streams, those rivers of a fast-moving air in the upper troposphere, play crucial roles in the weather patterns across the middle latitudes. The polar jet stream, flowing between 30 and 60 degrees latitude in both hemispheres, marks the boundary between cold polar air and warmer tropical air. Its meandering path, sometimes dipping far southward in deep troughs or bulging northward in high ridges, guides the movement of weather systems across continents. When the jet stream's path becomes locked in place for weeks, it can create persistent weather patterns, heat waves, drought, or prolonged rainfall that can stress natural systems and human infrastructure. Heat waves, periods of abnormally hot weather lasting from days to weeks, form when high-pressure systems trap warm air in place. The sinking air in these systems compresses and warms further, while clear skies allow strong solar heating. Without a cloud cover, nights provide little relief as the day's heat radiates slowly back to space. Urban areas, with their concrete, asphalt, and limited vegetation, can be significantly warmer than surrounding countryside, a phenomenon known as the urban heat island effect. During severe heat waves, this effect can make cities particularly dangerous for vulnerable populations. Drought develops not as a sudden event but as a gradual process when precipitation falls below normal levels for extended periods. Its effects accumulate slowly. Soil dries, plants wither, streams and reservoirs shrink. Meteorological drought, lack of precipitation, can progress to agricultural drought, soil moisture deficits, and then to hydrological drought, reduced water in streams and aquifers. Severe droughts have shaped human history, contributing to the collapse of civilizations from the Maya to the Anasazi. Modern societies, with their complex water management systems, are more resilient but still vulnerable to prolonged dry periods. At the other extreme, floods occur when water overflows normal channels. Flash floods develop rapidly, especially in steep terrain where rainfall cannot soak into the ground but rushes downhill in growing torrents. River floods build more slowly as water from vast watersheds funnels into main channels, sometimes cresting days after the rain that caused them has stopped. Coastal flooding can result from storm surges driven by hurricanes or from combinations of high tides, onshore winds, and low atmospheric pressure. Each type presents different hazards and requires different responses. Weather connected the human condition to the natural world. There is no escaping it. From our earliest history, weather has dictated the rhythm of our lives. Before gaslight or electric light, darkness fell with sunset. Before central heating, winter meant gathering around the hearth. Before air conditioning, summer heat drove people to seek shade and slow their pace. These fundamental experiences, the chill of evening, the relief of a cooling breeze, the smell of approaching rain, connect us across time to our ancestors and across space to all who share this atmosphere with us. In this journey through Earth's weather, we have touched on phenomena from the gentle formation of dew to the fury of hurricanes, from the quiet beauty of snowfall to the electrical drama of lightning. Weather surrounds us every day of our lives, influencing our activities, our moods, even our language and art. It operates on scales from the microscopic processes that form individual raindrops to global patterns that circle the planet. And though we have developed sophisticated tools to observe, understand, and predict weather, it retains a capacity to surprise and awe us. Perhaps nowhere is this more evident than in the phenomenon of thundersnow, that rare and magical occurrence when thunder and lightning accompany snowfall. It happens when the atmosphere develops layers of instability similar to those that create thunderstorms, but at temperatures cold enough for precipitation to fall as snow rather than rain. The snow muffles the thunder's sound, making it seem more distant, more mysterious. Those who have experienced thunders now speak of its otherworldly quality, a convergence of elements that seems to defy the ordinary boundaries of weather. Lightning illuminates the falling snow from within, creating moments of brilliant white clarity amid the darkness. The weather's capacity to create such extraordinary moments extends to the phenomenon of steam fog, sometimes called sea smoke. This occurs when cold air moves over significantly warmer water. The contrast causes the water to evaporate rapidly, but the moisture immediately condenses in the cold air above, creating wisps of fog that dance and swirl just above the surface. Seen at dawn on lakes, rivers, or oceans, steam fog creates landscapes of ethereal beauty, where the boundary between water and air becomes a realm of constant transformation. Early morning paddlers or fishermen might find themselves floating through these ghostly tendrils, partially visible, partially hidden, in a world neither fully solid nor fully vapor. Weather shapes the land itself through processes both gradual and sudden. Wind sculpts sand dunes into rippled crescents and stars. Rain carves channels that grow into streams and eventually rivers. Freeze-thaw cycles crack rocks, gradually reducing mountains to rubble. Lightning strikes can melt sand into glass tubes called fulgurites. Hailstorms strip leaves from trees and pound crops into the soil. These forces have been at work for billions of years, crafting landscapes long before humans existed to observe them. The weather we experience today continues this ancient work of shaping and reshaping the Earth's surface, a slow but relentless sculptor working in elements of air and water. Within the grand cycles of weather existed smaller, more localized phenomena that create their own microclimates. A forest maintains higher humidity than surrounding open areas, moderating temperature extremes and sometimes generating its own rainfall through transpiration. A city creates an urban heat island, trapping warmth in concrete and asphalt. A lake cools the land around it in summer and warms it in winter. These local variations demonstrate how weather is not simply imposed from above, but emerges from a conversation between atmosphere, land, water, and living things. The maple tree in your yard, the asphalt of your street, the lake beyond the town, each plays a role in shaping the weather you experience. Among weather's most mesmerizing displays are mammatus clouds, those hanging pouches that sometimes appear on the underside of anvil clouds after severe thunderstorms. They form when pockets of cold, dense air sink into warmer surroundings, creating the distinctive bulges. Though they appear ominous, they typically signal that the most intense part of the storm has passed. Their otherworldly appearance against the evening sky, often illuminated by the setting sun in oranges and pinks, creates scenes of such dramatic beauty that they seem almost painted rather than naturally formed. They remind us that within the atmosphere's violence can emerge moments of extraordinary aesthetic power. The morning after a heavy frost presents another kind of atmospheric artistry as ice crystals transform ordinary landscapes into glittering wonderlands. Frost forms when water vapor in the air deposits directly onto surfaces that have cooled below freezing, bypassing the liquid state in a process called deposition. Unlike dew, which condenses as liquid, frost builds crystal by crystal, creating intricate patterns on windows, leaves, and grass. Hoarfrost, which develops when moisture freezes on objects on clear, cold nights, can grow into feathery white structures that stand out from surfaces, catching the light like millions of tiny prisms. These crystalline formations last only until the sun warms them, a temporary transformation that makes their beauty all the more precious. Weather influences not just the physical world, but human creativity as well. Artists have long drawn inspiration from atmospheric conditions. Think of Turner's luminous skies, Van Gogh's swirling stars, Hokusai's great wave. Composers have evoked weather in music, from Vivaldi's Four Seasons to Debussy's La Mer to Beethoven's stormy passages in the Sixth Symphony. Writers from Shakespeare to Steinbeck have used weather as both a setting and metaphor. Our languages are rich with weather imagery. We rain on someone's parade, experience the calm before the storm, or have sunny dispositions. This pervasive influence reflects weather's fundamental role in a human experience, a constant companion to our lives that shapes not just our environment but our imagination. The blue of the sky itself is a weather phenomenon, a product of sunlight interacting with our atmosphere. Air molecules scatter short-wavelength blue light more effectively than longer wavelengths, sending blue light in all directions while allowing other colors to pass more directly through. Without an atmosphere, the sky would appear black, as it does on the moon. The changing colors of the sky, the deep blue of midday, the pale blue near the horizon, the reds and oranges of sunset, all result from light's journey through different thicknesses of air, scattered and filtered in varying ways depending on the sun's position and atmospheric conditions. Even this most familiar aspect of weather, the blue above us, embodies complex physics that connects Earth to the larger cosmos. High above the weather we directly experience, in the mesosphere 50 to 80 miles up, float the most ephemeral of clouds, noctilucent or night-shining clouds. These ghostly blue-white wisps can only be seen during the deep twilight when the sun has set at the surface but still illuminates these highest of clouds. They form around meteor dust at temperatures approaching negative 150 degrees Fahrenheit, making them the coldest natural features on Earth. First observed in 1885, they have become more common and more widespread in recent decades, possibly due to changes in the upper atmosphere. Seen from northern latitudes on summer nights, they shimmer like luminous silk against the darkening sky. Even higher, at the boundary between atmosphere and space, occurs one of nature's most spectacular light shows, the aurora. When energetic particles from the sun, carried by the solar wind, interact with oxygen and nitrogen in the upper atmosphere, they cause these gases to emit light. The result is curtains and rays of color, predominantly green but sometimes red, blue or purple, that dance across the polar skies. Indigenous peoples of the far north have many stories about these lights. Some see them as the spirits of ancestors, others as celestial animals, still others as the reflection of heavenly fires. The scientific explanation, involving solar particles, magnetic fields, and atmospheric excitation, does nothing to diminish their wonder. Weather extends beyond our own planet. Mars experiences dust storms that can engulf the entire planet. Jupiter's Great Red Spot is a storm larger than Earth that has persisted for at least 400 years. Venus is shrouded in sulfuric acid clouds that create a runaway greenhouse effect, making its surface hot enough to melt lead. Titan, Saturn's largest moon, has methane rain and rivers of liquid natural gas. Each world in our solar system has its own atmospheric dynamics, its own weather patterns, shaped by its particular mix of gases, its distance from the sun, its rotation rate, and many other factors. Studying these alien weather systems helps us better understand our own, placing Earth's atmosphere in a broader context. Back on Earth, the interplay of wind and water creates distinctive wave patterns on oceans and lakes. When wind blows across a water surface, it transfers energy through friction, creating ripples that grow into waves. The longer the fetch, the distance over which the wind blows, the larger the waves can become. In the open ocean, waves can build to enormous heights during storms, with the largest reliably measured wave reaching 29 meters (95 feet) during a 2020 extratropical cyclone in the North Atlantic. Such monster waves are relatively rare, but waves of 7 to 10 meters (23 to 33 feet) are common during strong storms. These rolling mountains of water demonstrate the immense energy transfer that occurs between atmosphere and ocean. Closer to shore, waves interact with the seafloor, changing their shape and behavior. As the bottom of a wave slows due to friction with the seabed, the top continues at its original speed, causing the wave to grow steeper until it breaks. This creates the white-capped breakers beloved by surfers and the rhythmic wash of surf on beaches. The sound of these waves, a constant background of white noise punctuated by the crash of larger breakers, has lulled countless people to sleep, whether in beachside homes or through recordings played in bedrooms far from any coast. There is something primordially soothing about this sound, perhaps connecting us to our evolutionary past or to the rhythmic heartbeat we heard in the womb. The meeting of warm and cold ocean currents creates some of the world's most productive fishing grounds, as well as some of its most challenging weather. When the cold Labrador Current meets the warm Gulf Stream off the coast of Newfoundland, for instance, fog frequently forms as warm moist air cools over the colder water. This region, including the Grand Banks, is notorious for its thick fogs and rough seas, but also for the abundance of marine life supported by the nutrient mixing that occurs at this boundary. Similar confluences occur off the coast of Japan, Chile, and Namibia, each creating its own characteristic weather patterns and marine ecosystems. These oceanic boundaries are like weather factories, generating distinctive atmospheric conditions that can extend far inland. Sand and dust storms represent another dramatic interface between land and atmosphere. When strong winds blow across dry, loose soil, they can lift fine particles high into the air, creating walls of sand and dust that reduce visibility to near zero and turn day into eerie twilight. The largest of these storms, called haboobs, can tower thousands of feet high and travel for hundreds of miles. They are most common in arid and semi-arid regions like the Sahel, the Arabian Peninsula, parts of Australia, and the southwestern United States. Beyond their immediate impact on visibility and air quality, these storms transport minerals across great distances, fertilizing distant ecosystems with the nutrients from other regions. Saharan dust, for instance, helps sustain the Amazon rainforest and provides minerals to Caribbean soils. The relationship between weather and living things extends far beyond humans. Plants have evolved countless adaptations to local climate conditions, from the waxy leaves of desert succulents that reduce water loss to the flexible stems of trees in windy areas that bend rather than break. Animals likewise show adaptations to weather, migration to avoid seasonal extremes, hibernation to conserve energy during cold periods, behavioral changes like seeking shade or burrowing to escape heat. Weather shapes the distribution of species across the planet, influencing everything from body size, larger in colder climates, smaller in warmer ones according to Bergmann's rule, to coloration, darker in humid areas, lighter in dry ones, following Gloger's rule. Insects, with their small size and often brief lifespans, are particularly attuned to weather conditions. Many can sense the subtle changes in barometric pressure that precede storms and will alter their behavior accordingly. Honeybees return to their hives before rain, ants seal the entrances to their nests or move their eggs deeper underground when heavy rain threatens. Some butterflies seek a shelter under leaves. These behaviors have evolved over millions of years as responses to the risks that changing weather conditions pose to these small creatures. Some farmers and gardeners still watch insect behavior as a guide to short-term weather prediction, continuing a tradition of observation that predates modern meteorology. Birds, with their ability to fly, have perhaps the most visible responses to weather changes. Many species time their migrations to coincide with seasonal shifts in weather patterns, taking advantage of favorable winds to assist their long-distance journeys. During extreme weather, birds may fly ahead of storms, seek shelter, or even fly into the calm eye of a hurricane. Seabirds like petrels and albatrosses have evolved to use the strong winds associated with the storms for efficient flight, soaring on updrafts, and riding air currents with the minimal energy expenditure. Some birds, like the American robin, are watched as harbingers of spring, their northward movement tracking the retreat of freezing temperatures and snow cover. Even marine life responds to weather, though we might not immediately associate underwater creatures with atmospheric conditions. Changes in wind patterns can cause upwelling of nutrient-rich water from the depths, triggering blooms of phytoplankton that support entire food webs. Storms mix the water column, redistributing oxygen and nutrients. Some fish spawn in response to specific weather conditions. The annual coral spawning on the Great Barrier Reef, for instance, occurs after the full moon in late spring, when water temperatures reach a certain threshold. Weather connects the sky to the sea through these complex ecological relationships, influencing life even in environments that seem removed from atmospheric influence. Weather leaves its mark in the geological record, allowing scientists to reconstruct ancient climate conditions. Annual layers in lake sediments, ice cores, and tree rings provide information about past temperature, precipitation, and even wind patterns. These paleoclimate records reveal that Earth has experienced dramatic weather changes throughout its history. Ice ages when glaciers covered much of the northern hemisphere, warm periods when palm trees grew in the Arctic, times of extended drought that changed the course of civilizations. By studying these records, scientists gain perspective on current weather patterns and climate trends, placing present conditions within the context of Earth's long environmental history. The intersection of weather and human history is particularly evident in agriculture, our species' foundational technology. The earliest farming systems emerged in regions with a reliable rainfall or river flooding, like the Fertile Crescent and the Nile Valley. Seasonal monsoons shaped the development of agriculture in South and East Asia, while the Mediterranean climate, with its wet winters and dry summers, favored certain crops like olives, wheat, and grapes. Farmers everywhere developed traditions and technologies to work with their local weather patterns, terracing to manage heavy rainfall on slopes, irrigation to survive dry periods, windbreaks to protect crops from damaging winds. These adaptations became embedded in cultural practices, religious calendars, and folk wisdom. Weather-related disasters have repeatedly altered the course of human affairs. The Little Ice Age, a period of cooling that affected various regions between roughly 1300 and 1850 CE, contributed to crop failures, famine, and social unrest in Europe. A series of monsoon failures in India during the late 1800s, exacerbated by colonial policies, led to catastrophic famines that killed millions. The Dust Bowl of the 1930s forced mass migration from the American Great Plains. More recently, events like Hurricane Katrina in 2005 and Superstorm Sandy in 2012 have demonstrated how extreme weather can overwhelm even modern infrastructure, causing long-lasting social and economic disruption. These events remind us that despite all our technological advancement, weather remains a powerful force in human affairs. Throughout history, humans have attempted not just to predict weather, but to control it. Ancient practices included prayer, ritual, and sacrifice directed at weather deities. Modern efforts have been more technological, including cloud seeding to induce rainfall by introducing particles like silver iodide into clouds, providing additional condensation nuclei. Results from these efforts have been mixed, with some studies showing modest increases in precipitation under specific conditions, while others show little effect. More ambitious proposals to mitigate climate change through geoengineering, such as injecting reflective particles into the stratosphere to reduce incoming solar radiation, remain highly controversial due to potential unintended consequences and questions of governance. Weather modification highlights the tension between human desire for control and the immense complexity of atmospheric systems. Our understanding of weather has evolved dramatically over human history. Ancient civilizations identified patterns and developed rich mythologies to explain atmospheric phenomena. The Greeks associated different weather conditions with specific gods. Zeus hurled thunderbolts, Aiolos controlled the winds, Iris created rainbows. Similar personifications appeared in cultures worldwide. More systematic observation began in ancient China, where records of rainfall, floods, and droughts date back thousands of years. The invention of weather instruments in Renaissance Europe, the thermometer, barometer, hygrometer, and anemometer allowed for quantitative measurement rather than just a qualitative description, laying the groundwork for modern meteorology. The 19th century brought crucial advances in weather science. The telegraph allowed observations to be collected from distant locations and assembled into the first weather maps, revealing the movement of weather systems across continents. Scientists began to understand the physics of atmospheric processes, the gas laws, thermodynamics, fluid dynamics. By the early 20th century, Norwegian meteorologist Wilhelm Bjerknes and his colleagues had developed the concept of air masses and fronts, creating the foundation of modern weather analysis. These advances made possible the first scientific weather forecasts, though their accuracy and range remained limited. The most dramatic improvements in weather forecasting came after World War II with the development of computers, radar, and satellites. The first numerical weather prediction using a computer was performed in 1950, though the calculation took longer than the actual weather took to occur. Today's supercomputers can process vast amounts of observational data and run complex models that simulate atmospheric physics with increasing fidelity. Weather satellites provide continuous global monitoring, while networks of weather radars track precipitation in real time. These technologies have extended reliable forecasts from just a day or two to about a week, with general trends predictable even further into the future. Despite these advances, the atmosphere remains a challenging system to predict precisely. It exhibits chaotic behavior, where tiny differences in initial conditions can lead to vastly different outcomes over time. The famous butterfly effect, described by the mathematician and meteorologist Edward Lorenz. To address this inherent uncertainty, meteorologists now use ensemble forecasting, running multiple simulations with slightly different starting conditions to generate a range of possible outcomes. This approach provides not just a prediction of what the weather will be, but an assessment of the forecast's reliability and the likelihood of different scenarios. It acknowledges that some degree of uncertainty is intrinsic to weather prediction, not merely a limitation of current methods. As our understanding of weather has grown more sophisticated, so has our awareness of its connections to broader climate patterns. Weather is the short-term state of the atmosphere in a particular place, the temperature, humidity, wind, and precipitation on a given day. Climate is the long-term average of weather over time, typically at least 30 years. While an unseasonably cool day doesn't contradict global warming trends, persistent changes in weather patterns over decades do signal climate change. The boundary between weather and climate is not sharp but exists along a continuum of timescales, with phenomena like El Niño occupying a middle ground as they operate over months to years. Climate change is altering weather patterns worldwide in complex ways. As the atmosphere warms, it can hold more moisture, about 7% more for each degree Celsius of warming, leading to more intense precipitation events when conditions are favorable for rain or snow. At the same time, higher temperatures increase evaporation rates, which can exacerbate drought conditions in dry areas. Heat waves are becoming more frequent and intense, while cold extremes are becoming less common, though still possible. These changes don't occur uniformly across the globe, but vary by region and season, creating a complex patchwork of impacts that scientists are working to understand and predict. Extreme weather events like hurricanes, floods, and droughts have always occurred naturally, but climate change is altering their frequency, intensity, and distribution. Attribution science, the study of how climate change affects specific weather events, has advanced significantly in recent years, allowing scientists to quantify the influence of human-caused warming on particular extremes. While no single storm or heat wave is simply caused by climate change, many now occur in an environment significantly altered by human activities, making them more severe or more likely than they would have been in the past. This growing field helps connect abstract climate trends to concrete weather impacts that people experience directly. Weather and climate influence each other through feedback loops that can amplify or dampen changes. For example, as Arctic sea ice melts due to warming temperatures, the darker ocean surface absorbs more solar energy than the reflective ice did, leading to further warming, a positive feedback. Clouds can provide either positive or negative feedbacks depending on their type and altitude. Low, thick clouds primarily reflect sunlight back to space, cooling, while high, thin clouds mainly trap heat, warming. These feedbacks operate across various timescales, from days to decades, creating complex interactions between short-term weather and long-term climate trends. Understanding these connections is essential for improving both weather forecasts and climate projections. Weather communication has evolved along with weather science, from simple storm warnings to detailed multimedia forecasts. Early warning systems now provide advance notice of hazardous conditions, from minutes for tornadoes to days for hurricanes, saving countless lives. But effective communication involves more than just scientific accuracy. It requires translating complex meteorological information into terms relevant to people's daily decisions. Should I carry an umbrella, cancel the picnic, evacuate my home? Weather communicators must balance technical precision with practical utility, providing information people can understand and act upon. This challenge has grown as forecast products have become more sophisticated, offering probability distributions rather than simple yes-no predictions. The aesthetic dimensions of weather enrich our lives in countless ways. A crystal-clear winter day with fresh snow glittering in sunshine. A summer evening when the light turns golden before a thunderstorm. The particular quality of air just after rain, fresh and charged with negative ions. The sight of distant weather moving across a landscape, a curtain of rain beneath dark clouds, sunlight breaking through in shafts. These experiences engage all our senses and connect us to the larger natural world. They remind us that for all our sheltered modern lives, we remain embedded in atmospheric processes that transcend human scale and control. Fog creates some of weather's most evocative scenes, transforming familiar landscapes into mysterious realms where distance becomes uncertain and sounds travel differently. It forms when water vapor condenses into tiny droplets suspended in air, reducing visibility and diffusing light. Valley fog pools in low areas on clear, calm nights as cooled air sinks and chills to its dew point. Advection fog forms when warm moist air moves over colder surfaces, common along coastlines where warm air from land passes over cool ocean water. Sea fog, or R, can move inland like a slow-motion wave, swallowing houses, trees and hills as it advances. In mountain valleys, fog can persist for days in winter, trapped by temperature inversions where warmer air aloft prevents vertical mixing. Snow transforms landscapes not just visually but acoustically, creating a distinctive hush as the crystalline structure absorbs sound waves. The quality of snow varies tremendously depending on temperature, humidity, and wind conditions during formation and after falling. Powder snow, composed of small, dry crystals with minimal moisture, creates the champagne skiing prized by winter sports enthusiasts. Wet, heavy snow clings to branches and power lines, creating hazards but also scenes of pristine beauty. Graupel, sometimes called soft hail, forms when supercooled water droplets freeze onto falling snowflakes, creating small, opaque pellets. Each type of snow interacts differently with light, with wind, with surfaces, creating unique conditions that those who live in snowy regions learn to distinguish and name. The sound of weather provides its own rich vocabulary of experience. Rain patters on leaves, drumming soft rhythms that change with intensity. Wind whispers through grass, whistles around buildings, roars through mountain passes, each sound conveying information about its strength and direction. Thunder rumbles, crashes, or cracks depending on the lightning's distance and the atmospheric conditions through which the sound travels. Snow falls in near silence, but creaks and squeaks underfoot at different temperatures. These acoustic dimensions of weather connect us to our environment in immediate, visceral ways that precede language and analysis. Long before we understood the physics of sound waves, humans listened to weather and learned from what they heard. The smell of weather is equally evocative. The fresh scent after rain, petrichor, comes from oils released by dry soil when it gets wet, combined with geosmin, a compound produced by certain bacteria. The distinctive aroma that often precedes rain comes from ozone formed by lightning and carried ahead of the rain by downdrafts, along with plant oils released by leaves in response to increasing humidity. The clean smell of air after a thunderstorm results from the washing away of pollutants and the creation of negative ions. These olfactory experiences trigger powerful memories and emotions, connecting us to past weather events in ways that visual recollections alone cannot match. They are part of our species' long history of reading atmospheric conditions through multiple senses. Beyond their practical importance, weather phenomena have profound cultural and symbolic dimensions. Rainbows appear in mythologies worldwide as bridges between earth and heaven in Norse tradition, as the embodiment of the divine messenger Iris in Greek mythology, as a sign of divine covenant in Judeo-Christian texts. Storms symbolize chaos and divine power in countless traditions, while clear skies represent order and divine favor. The four winds were personified in many ancient cultures, each with its own character and associations. These weather symbols permeate literature, art, and religious imagery, forming a rich cultural vocabulary that connects atmospheric phenomena to human meaning-making. Even as scientific understanding has advanced, these symbolic associations persist, testifying to weather's deep psychological significance. For countless generations, weather knowledge was preserved and transmitted through oral traditions, proverbs, and sayings. Many of these contain genuine meteorological insights. Red sky at night, sailors delight. Red sky in morning, sailors take warning. Reflects the fact that weather systems typically move from west to east in middle latitudes, so a red sunset, western sky often indicates clear air to the west that will arrive overnight, while a red sunrise, eastern sky, suggests moisture-laden air that may bring storms. Mackerel sky and mare's tails make tall ships carry low sails recognizes that cirrocumulus and cirrus clouds often precede storms. These folklore predictions are being re-evaluated by modern meteorologists, who find that many contain valid observational wisdom embedded in memorable, transmissible forms. Indigenous weather knowledge represents some of the most sophisticated traditional meteorology, developed through centuries of careful observation in specific local environments. Aboriginal Australians recognize subtle seasonal changes marked by the flowering of certain plants, the appearance of particular insects, or shifts in animal behavior, far more nuanced than the four-season calendar used in temperate Europe. Pacific Islanders developed extensive knowledge of ocean currents, wind patterns, and cloud formations that enabled long-distance navigation without instruments. Inuit people identified dozens of different snow and ice conditions, each with specific implications for travel and hunting. These knowledge systems are increasingly recognized not as primitive alternatives to modern meteorology, but as complementary approaches with particular strengths in understanding local conditions and subtle environmental indicators. The field of biometeorology studies the relationship between weather and living organisms, including humans. Seasonal affective disorder, which causes depression symptoms during darker winter months, appears linked to changes in light levels and their effect on circadian rhythms. Some people report increased joint pain before storms, possibly related to changes in barometric pressure. Hot, humid conditions can exacerbate respiratory problems, while extremely cold, dry airs can irritate airways. Beyond these direct physiological effects, weather influences behavior. People tend to be more aggressive during hot weather and more lethargic during prolonged cloudy periods. These connections between atmosphere and body, mood and weather remind us that humans remain biological organisms responsive to our physical environment despite our climate-controlled buildings and weather apps. Weather influences architecture in profound ways. Traditional building forms evolved to work with local climate conditions. Thick adobe walls in hot, dry regions that keep interiors cool during the day and release heat at night. Steep roofs in snowy areas that shed heavy accumulations. Raised structures in flood-prone regions. Courtyards that create microclimates of shade and captured breezes in hot climates. Modern architecture often relies on mechanical systems to create comfort rather than passive design strategies, but interest in climate-responsive building has revived as energy concerns have grown. Architects now use computational fluid dynamics to model how wind will flow around and through buildings and how sunlight will strike surfaces throughout the year, creating designs that work in harmony with the local weather patterns rather than against them. Weather has shaped transportation throughout human history. Sailing vessels depended entirely on wind, leading to deep knowledge of seasonal patterns and prevailing currents. Early aviation was highly vulnerable to weather conditions, with fog, storms, and icing posing serious hazards. Even modern transportation systems remain weather-sensitive. Aircraft must avoid thunderstorms and icing conditions. Ships alter course to avoid major storms. Trains reduce speed in extreme heat that can warp rails, and roads become hazardous with ice or flooding. Weather disruptions to transportation cascade through economic systems, affecting supply chains, business operations, and daily commutes. These vulnerabilities remind us that despite technological advances, weather continues to influence human movement across the planet. The interface between weather and energy systems grows increasingly important as renewable energy sources like wind and solar become more prevalent. Unlike fossil fuel power plants that can operate regardless of atmospheric conditions, renewables are inherently weather-dependent. Wind turbines need wind, but not too much. Solar panels need sunlight, and hydroelectric dams need adequate rainfall in their watersheds. This creates new connections between energy security and weather prediction, requiring more detailed forecasts of wind, cloud cover, and precipitation patterns. It also drives interest in energy storage technologies that can buffer the variability of weather-dependent sources, ensuring reliable power despite fluctuating production. As the energy transition progresses, weather and climate information becomes a crucial infrastructure for planning and operating power systems. Agriculture remains perhaps the most weather-dependent of all human activities, with crops and livestock directly exposed to atmospheric conditions. Modern farming uses increasingly sophisticated weather information, not just forecasts, but specialized products like growing degree day calculations, drought indices, and frost predictions. Precision agriculture matches planting, irrigation, and harvesting to microscale weather variations across fields. Climate services provide seasonal outlooks to help farmers select crops and varieties suited to anticipated conditions. Despite these advances, extreme weather events like drought, flood, hail, and unseasonable frost continue to pose significant risks to food production worldwide. The fundamental connection between weather and food security remains as strong today as it was for the first farmers thousands of years ago. Weather connects us to the planet's larger rhythms in ways that few other natural phenomena do. It reminds us that despite all our technology, we remain part of Earth's systems, affected by the exchange of energy between sun, atmosphere, and surface, influenced by the planet's rotation and the resulting Coriolis effect, subject to the hydrological cycle that moves water between ocean, air, and land. Weather transcends human boundaries, flowing across borders without regard for political divisions. A storm forming over the Pacific will affect North America days later. Saharan dust fertilizes the Amazon. Arctic warming alters jet stream patterns that influence weather in Europe and Asia. These connections embed us in planetary processes that operate on scales both vastly larger and much smaller than human experience. The unpredictability of weather has shaped human psychology in profound ways. It has taught us to live with uncertainty, to make contingency plans, to notice subtle environmental cues. Agricultural societies developed rituals and offerings to weather deities not just as a supernatural insurance, but as ways of managing anxiety about forces beyond their control. Modern weather forecasts serve a similar psychological function, helping us prepare practically while also reducing the stress of uncertainty. The familiar ritual of checking the weather forecast, whether via newspaper, television, or smartphone app, provides a sense of orientation to the day ahead, a frame for expectations, a way of situating ourselves in time and space. We cannot control the weather, but knowing what to expect helps us feel more in command of our lives. In an age of climate change, weather takes on new significance as the medium through which most people experience larger environmental shifts. An individual heat wave, flood, or drought cannot be simply attributed to climate change, but the increasing frequency and intensity of such events make abstract global warming trends concrete and immediate. This creates both challenges and opportunities for communication. On one hand, the inherent variability of weather can make climate trends difficult to perceive directly. A cold snap seems to contradict warming, though it may actually result from altered jet stream patterns due to Arctic warming. On the other hand, extreme weather events can make climate change tangible in ways that graphs and statistics cannot, creating moments when the long-term changes become viscerally real. Weather photography and videography have exploded in recent decades, from dramatic lightning captures to time-lapse cloud formations, from satellite imagery of hurricane eyes to the airborne adventures of storm chasers. These visual documents serve scientific purposes, helping meteorologists understand atmospheric processes, but they also connect people emotionally to weather as a source of awe and beauty. The popularity of weather imagery on social media platforms, sunset photos, storm clouds, frost patterns, rainbow sightings, suggests a widespread appreciation for atmospheric aesthetics that crosses cultural boundaries. In a world where many people spend most of their time indoors, these images maintain a connection to the sky's ever-changing canvas and the elemental forces that shape it. The poetry of weather appears in languages worldwide, capturing atmospheric states that might otherwise elude description. The Welsh have glow man, a light but persistent rain somewhere between drizzle and shower. Portuguese offers saudade, a yearning melancholy that corresponds to certain misty gray days. Japanese gives us komorebi, the dappled light that filters through tree leaves on a sunny day, and yugen, the profound feeling evoked by watching geese disappear into a cloud bank. These terms encode not just meteorological conditions, but their emotional and aesthetic dimensions, preserving cultural responses to weather that have developed over generations in particular landscapes. They remind us that weather is not just a physical phenomenon, but a deeply human experience filtered through perception, memory, and language. As our exploration of weather draws toward its close, we return to a fundamental truth. Weather is the most democratic of natural phenomena, experienced by everyone, everywhere, every day. It may affect us differently depending on our shelter, clothing, occupation, and location, but no one escapes its influence entirely. It connects the banker in her skyscraper to the farmer in his field, the child in the schoolyard, to the elder in the nursing home. Weather is perhaps the last wild element in many modern lives, the final reminder that despite all our technological achievements, we remain part of larger natural systems that operate according to their own principles. In this shared experience lies both vulnerability and connection. We are all ultimately under the same sky. Weather's constant change mirrors the impermanence at the heart of existence. Nothing in the atmosphere remains fixed. Clouds form, transform, and dissipate. Winds strengthen, shift, and calm. Temperatures rise and fall. Pressure systems come and go. Even the steadiest rainfall eventually ends. The most persistent fog eventually lifts. The longest drought eventually breaks. In this ceaseless flux, we might find a model for approaching life itself, appreciating what is present now, knowing it will change, remaining curious about what comes next. The atmosphere teaches patience in the face of conditions we cannot control and adaptability in response to inevitable change. These are lessons as relevant to human affairs as they are to outdoor plans. As you rest tonight, perhaps there is weather just outside your window, rain tapping gently on the roof, wind sighing through trees, snow falling silently in the darkness, or simply the still air of a calm night. Whatever conditions prevail, they connect this moment to the planet's ancient rhythms, to the endless dance of elements that has continued since the Earth first formed an atmosphere billions of years ago. The same physical principles that create the grandeur of a supercell thunderstorm or the delicacy of a snowflake are at work in this moment, on this night, in the air that surrounds you as you drift towards sleep. Weather will continue its endless variations while you sleep, while you dream. The atmosphere never rests, never pauses in its fluid movements, its constant exchanges of energy and moisture. Somewhere rain is falling, somewhere lightning flashes, somewhere gentle breezes stir leaves, somewhere fog is lifting to reveal mountains. Somewhere snow crystals are forming in high clouds. All of these phenomena, from the violent to the serene, from the common to the rare, are expressions of the same atmospheric physics, the same fundamental processes playing out in countless variations across the face of our planet. The study of weather connects some of the smallest structures in our atmosphere, water molecules, dust particles, air ions, to some of the largest, global circulation patterns, jet streams, planetary waves,